Welcome to demo number 0, Threat Prediction. In this demonstration, we present the horse threat prediction workflow, showing how different components collaborate to anticipate potential threats and prepare preventive actions through coordinated communication across the architecture. The purpose of this demo is to validate the integration between modules by focusing on the exchange of messages across the horse components. Rather than demonstrating a real preventive scenario, this workflow acts as a functional validation, similar to a connectivity test, ensuring that all modules can communicate correctly. To trigger the workflow, a simulated DDoS_downlink attack is considered, together with the preventive strategy block_pot_address, which allows the system to generate and propagate the required messages between components. This slide shows the complete threat prediction workflow. The process starts with infrastructure monitoring and data collection, followed by pre-processing and anonymization stages that prepare the information for analysis. The prediction and impact analysis components evaluate the potential evolution of the detected threat and generate a preventive intent. This intent is then validated, translated into technical actions, and finally prepared for deployment within the infrastructure. Next, we will go through this workflow step by step, showing how messages are exchanged between the different horse components throughout the process. In this part of the workflow, the interaction between the infrastructure and the smart monitoring component is shown. The infrastructure generates monitoring measurements that are collected by smart monitoring, which acts as the entry point for operational data within the horse architecture. Smart monitoring stores this information in Elasticsearch, allowing the data to be indexed and queried later by the following components in the workflow, enabling the threat prediction process to begin. In this stage, smart monitoring exchanges data with the preprocessing module and the privacy anonymization gateway. As in the threat detection workflow shown in demo number 0, the collected raw data is first processed and normalized and then anonymized. At this point in the workflow, smart monitoring forwards the processed and anonymized data to two key analytical components: the early modeling module and the profiling and prediction network digital twin or PNP-NDT. The early modeling module receives the relevant threat-related information and starts building a contextual model of the detected situation. Once the attack model is generated, early modeling sends this structured representation to the PNP-NDT. In the video, we can observe how the modeled attack is successfully delivered to the digital twin, confirming that the message exchange between both components is correctly established. We now focus on the profiling and prediction network digital twin. The purpose of the component is to create a virtual representation of the network that allows the system to simulate and predict how a detected threat may evolve before it affects the real infrastructure. Using the contextual attack model generated by early modeling together with monitoring data, the PNP-NDT evaluates the potential impact and behavior of the simulated DDoS_downlink attack. It performs predictive analysis and generates the predicted attack, which is forwarded as structured output to the next decision-making components. In the video, the right side shows the visual connection between the PNP-NDT early modeling and the distributed trustable AI engine, highlighting its central role in the prediction phase. On the left side, the logs display the real-time message exchange, confirming that the digital twin receives, processes, and forwards the information correctly. Next, the output generated by the PNP-NDT is forwarded to the Distributed Trustable AI Engine, or DT. The DTE is responsible for performing intelligent analysis over the predicted threat scenario. It evaluates the information received from the digital twin and determines the appropriate preventive intent based on AI-driven reasoning. In the video, we can observe how the message coming from the PNP-NDT is successfully received by the DT. We now move to the Impact Assessment Network Digital Twin, or IA-NDT. This component receives the attack model generated by early modeling and evaluates its potential impact on the network. While the PNP-NDT predicts how the threat may evolve, the IA-NDT assesses how it could affect services, network functions, and infrastructure components. Using the DDoS_downlink scenario, it estimates possible service degradation and overall system exposure, translating the threat model into a concrete impact evaluation. Once the assessment is completed, the IANDT forwards the results to the intent-based interface, ensuring that preventive decisions are not only prediction-driven, but also impact-aware. In the video, we can observe the correct reception, processing, and forwarding of messages, confirming the proper integration of this component within the horse threat prediction workflow. The IBI receives the preventive intent generated by the DTE and the IANDT. At this point, the IBI interacts with the Common Knowledge Base, or CKB. The CKB serves as the shared repository of knowledge within HORSE. It contains information about known attacks, preventive strategies, historical records, and policy definitions. Through this exchange, the IBI validates and enriches the preventive intent using stored knowledge, ensuring consistency with previously defined strategies and system intelligence. The logs confirm that the consultation with the CKB is successfully completed before proceeding further in the workflow. We now move to the intent-based interface, or IBI. The IBI acts as the bridge between intelligent decision-making and operational execution within the HORSE architecture. It receives the preventive intent generated by the analytical components, including the outputs from the DTE and the IANDT, and translates this high-level intent into coordinated preventive workflows. At this stage, the system moves from analysis to orchestration logic. The IBI interprets the intent, identifies the required actions, and determines how these actions should be structured across different domains of the infrastructure. Rather than directly applying configurations, the IBI focuses on transforming strategic preventive decisions into structured operational requests that can later be validated and deployed. In the video, we can observe how the preventive intent reaches the IBI, how it is processed, and how new structured messages are generated to continue the workflow toward knowledge validation and compliance assessment. This confirms that the architecture is capable of translating AI-driven reasoning into actionable operational logic. Following this step, the workflow reaches the compliance assessment component, or CAS. The CAS verifies that the proposed preventive actions comply with security policies, regulatory constraints, and operational rules. This ensures that any action generated by the system is not only technically valid, but also aligned with governance and compliance requirements. In the video, we can see the message exchange confirming that the preventive intent has been assessed and approved before continuing to the execution phase. In the final stage of the workflow, the preventive intent reaches the Reliability, Trust and Resilience Provisioning component, or RTR. The RTR is responsible for transforming the validated intent into operational actions, defining the corresponding playbook that specifies how the preventive actions should be executed within the infrastructure. These actions are then forwarded to the EPM, the End-to-End Proactive Secure Connectivity Manager, which translates the defined strategy into concrete technical configurations ready for deployment. Finally, the DOC component applies these configurations across the infrastructure domains, completing the execution phase of the workflow. The detailed demonstration of these deployment steps can be observed in the demo number 0 threat detection video, where the preventive execution is shown in practice. With this demonstration, we have validated the end-to-end threat prediction message exchange across the HORSE architecture. Thank you for watching.